Okay, so in this lesson, we're going to discuss, we're still talking about systems of linear equations. We're going to talk about the differences between what makes up a consistent system versus an inconsistent system. And so let's divide those right now. So we've got consistent systems, and then we have inconsistent systems. And these two are somewhat different, although you really can't tell the difference when you start looking at equations until you do a couple of things. So I'll kind of give you the diagrams here, kind of tell you, discuss it generally, and then we'll throw up some equations of each different type. Within consistent systems, however, you have two separations. You have an independent system, and then you also have a dependent system. Kind of make this over here, dependent. So here's the division. You got consistent, inconsistent. With inconsistent, you have independent and dependent. Independent systems have only one answer, one solution, which basically means one ordered pair that will solve both equations. Dependent systems have infinitely many. And again, I will give you examples of these in each one. Dependent systems have infinitely many solutions, which means there's just infinite number of answers for that system. Inconsistent systems have no solution whatsoever. Oh, let me erase that real quick. That kind of came out wrong. No solution. So as we look at these ideas, I will pull up a graphic in the next one that kind of identifies what each of these systems looks like on a graph. Keep in mind, consistent, and I'll just highlight these, have two different ideas that you can think about: independent and dependent. And inconsistent is anything that has no answer or no solution is an inconsistent system. Let's go to an image that I have that kind of portrays what I'm talking about. Let me add that. All right, so I have this picture loaded here, and it kind of gives you examples of what each is. So you've got, just change pen color here real quick. No, I'm good there with the red. You have one solution, consistent and independent. Notice it highlights both of those, okay? Then you have infinitely many solutions, which is consistent again, but it's dependent. Now here's the idea. Anytime you have consistent, independent, you notice these two lines have an intersection right there. So whatever point that would be the solution of both of your equations, your systems of lines there. This one, although you only see one line here, an example of consistent dependent would be two lines right on top of each other. So I'd have the purple and the red line. They'd be exactly the same equation right on top of each other with the same y-intercept and everything similar. And that would be a consistent dependent. So here, intersecting, if I was to identify how to get these, the slope of consistent independent would be intersecting lines, which means the slopes would be different. Okay, for the coinciding lines, which is what they're talking about up here, obviously they're the same exact lines, so the slope would be the same. Also, what would be the same would be the same y-intercept. In essence, this is very simple. It'd be the same exact equation of the line. So you'd have two instances of the same equation of the line. Parallel lines on the other side over here would become there is no solution, which means that's the very definition of parallel lines. They do not intersect, so therefore there's no solutions whatsoever. So that's why it is inconsistent. Over here, you could have the same slope, but what would be different would be the y-intercepts would be different. Okay, so let's look at some examples. The reason I identify slope in all of these is that's going to kind of identify us as to how we organize our systems into these categories. So let's do an example. Book, I've got number 17, which has these two examples right here. 7x minus y equals 6, and then I have negative 7x plus y equals negative 6. And so let's break these off into slope-intercept form, see what they look like. Negative 7x plus y equals negative 6. I could go ahead and graph these things if I wanted to, but I won't. Let's just see how this works out. So I'm going to subtract 7x from both sides. and I got negative y equals negative 7x plus 6. So therefore y equals 7x minus 6. So there's my slope-intercept form for that one. Let's check out what this one does. If I add 7x to both sides, I get y equals 7x minus 6. So as I look at these two equations, I notice, I'll change pen color here, here's my slope for this one, 7. Here's my slope for this one. So I have two equations with the same slopes. Slopes are equal, but yet they are different y-intercepts. I got, oh, wait a minute. No, I'm sorry. I take that back. They're the same exact thing. I've got negative 6 and negative 6 here. Same exact equation here. I thought one was positive and one was negative. Same exact equation. So that basically means I have a dependent coinciding lines. So they are dependent. Okay. Let's do another one real quick just to give another example. Okay, let's try another one. Let's try 18. 18, I have negative 3x plus y equals 4, and x minus 1/3 y equals 1. Same thing here. I'm going to add 3x to both sides. So I get y equals 3x plus 4. Good to go there. I am going to subtract x from both sides to do this one. So I have negative 1/3 y equals negative x plus 1. So here's the tricky part. How do I get rid of the negative 1/3 right here, right? And how you do that is to multiply everything by negative 3. Because I know that negative 3 times negative 1/3 is canceled. It equals 1, so I'm left with y. Whatever I did to the y, I got to multiply negative 3 times everything. So I get a negative 3 times negative x is going to give me a 3x, and then negative 3 times 1 is going to give me a negative 3. So I'm actually good there. I've got two solid slope-intercept forms. Let's start looking at some things here. I got, oh, wait a minute, I got a 3 slope here and a 3 slope here, but I have different y-intercepts, which in essence means if I got the same slope, equal slopes, different y-intercepts, I can automatically tell you, based on my previous knowledge, these lines are parallel. Parallel lines are always inconsistent. They do not have a solution. No solution. Because I know by the definition of parallel, these lines never intersect, so therefore there is no solution. Let's look at number 20. Y equals 2x minus 1, and y equals negative 2x plus 5. There we go, two equations. I immediately look at this and I go, oh, wait a minute, this is going to be a little easier for me. They're already in slope-intercept form. So here we go looking at, so let's circle the slopes in red. Okay, and I notice I got two different, so I have negative 2 and 2 different slopes. So those are different. So let's look at y-intercepts now, because if I have different slopes with the same y-intercept, I look at y-intercepts, and those are different as well. So I know that these lines cross the y-axis at different places. I know they have different slopes. There is no other way to graph these lines than to realize that they do intersect with each other. So these are the ones that we've been working with for the most part. These two lines will intersect each other because they're different y-intercepts and different slopes. So therefore they are independent. And again, this is the most common. These are the ones that we've worked with over and over and over again.